So we discussed that you have a relativistic momentum equals gamma mu. Okay, and so relativistic for regular three-component force is the rate of change of relativistic momentum. And you can expand that as, that's not for force and for momentum. This is just the spatial component of the for momentum, regular momentum. And you can write that as ddt. Notice this is regular time. This is not proper time. This is just regular stuff, except that it's relativistic momentum. So that's m divided by this 1 u squared c squared times u. I'm doing this, well, this is in 3 dimensions, okay? And so you can basically say that this is the relativistic version of Newton's second law, right? You can no longer say F equals ma, okay? Because when you take a derivative of this, you'll have to take the derivative of this times this plus this times the derivative of this. It doesn't have the form of F equals ma anymore. So you could think of relativistic dynamics as obtained by taking classical dynamics and replacing a regular mass by this quantity right here. This used to be called relativistic mass, but that fell out of favor. You might remember the discussion that people thought, no, leave mechanics alone. It's E&M that has to be fixed. And Einstein insisted that, no, leave E&M alone. E&M is quite right. We'll have to fix mechanics. And here's how we fix mechanics. Okay, so let's look at an example of constant force in 1D. So this is going to be constant force F naught. What's an example of a particle moving in constant force? How about an electron between parallel plate capacitor, right? So this is a constant field. And you place an electron, and I guess this would be a proton. You place a positron, and it goes in the direction of the field. Okay, a good example of a constant force scenario. Okay. Note that constant force and constant acceleration are not the same thing anymore. You don't get a constant acceleration with a constant force. And so here's why, right? So you have F naught equals ddt of m gamma u, it's in 1D. You can integrate this. This is a constant, right? So this is a constant, 75 newtons. And so you integrate, and and you get F naught t plus some unknown constant equals m 1 minus u squared over c squared taken square root times u. Okay, if u initial equals 0, then c equals 0. If we start with 0 velocity, so when t equals 0, we want u to be 0, well then c has to be 0. The constant integration has to be 0. Constant integration is always fixed by initial data, initial conditions. Okay, so now invert to get not t of u, but u of t. And when you do the math, you get u of t. So this is what a velocity of a particle moving a constant force does. It would be F naught over m times u times t. Okay, that's regular mechanics. Constant force, speed gains linearly in time, like following a rock. However, sooner or later, this correction term will become important. It's an interesting little denominator. Now again, what do we do if we want to understand what this math says? Okay, is we plot it. So what I'm going to do is I'm going to plot what I'm going to do is I'm going to plot u over c. That will become clear. Okay, and so u over c can at max be 1, and this is f naught t over mc. It's like a dimensionalized time. And what happens then is initially you ramp up the speed at a constant rate, but then not so fast, okay? There's a universal speed limit. You cannot break through that barrier. So this is another sort of mechanistic explanation why u cannot be bigger than c. So I just gave you an energetic reason, and here's the force reason, that you have to, that no matter how long you're applying the force on the object, it becomes less and less efficient, sort of, okay? So this is the classical regime right here, and this is the full relativistic regime. And since we're at it, we can integrate this one more time. One more time to get x of t. Okay, so I'm going to say x of t equals, if not over m, I'm just going to take this constant outside of the integral. You all know and love how to do that. You do this. Okay, so this is t prime dt prime. Hope you understand why I'm putting the primes, because integration variable should not be confused with the upper limit. But if primes bother you, then just don't worry about it. Don't pay attention to the prime. And I'm just integrating this thing. And you should actually know how to do this integral, but don't worry, it's not ominous. I'm not going to ask you to do that on the exam. So what you get is you get the following. This is taking square root, quantity minus 1. Okay, and when I plot that, well, again, let me just plot. I can plot dimensionless variables, but just for the sake of simplicity, initially it grows parabolically, but then it switches into kind of a linear growth. Okay? In classical mechanics, if you apply a constant force, the position versus time grows parabolically, right? So like a particle, like a falling rock. So this is a parabola, and so this is classical. X is proportional to t squared, and this is classical. U is proportional to t. But then when you reach enough velocity, okay, the position doesn't grow as fast, because your velocity basically becomes essentially speed of light, and you just accelerating, and you stop accelerating, and you just basically coast along. So this is what's going on. You replace a parabola with a hyperbola, which approaches. This is kind of like approaches approximately CT as time goes on. Okay, and it takes a certain amount of time to go from classical regime to a relativistic regime. But let's not milk that. Okay, I don't want to confuse you. I just wanted to get across a few key points that while fundamentally you cannot break the speed of light barrier due to causality arguments, mechanistically, this is the reason of what prevents you from breaking the speed of light barrier. Okay, so that's what I wanted to say, and that's it. Okay, so folks, pat yourself on the back. We had very intense 3 weeks.